of an object in which of the following examples can you sense motion? How will you explain presence and absence of motion? 1. You are traveling in a bus. Is the person sitting next to you in motion? 2. What do you take into consideration to decide if an object is moving or not? You have learned that motion is a relative concept. If the position of an object is changing with respect to its surroundings, then it is said to be in motion. Otherwise, it is said to be at rest. We see the motion of several objects every day. Sometimes we cannot see the motion of an object directly, as in the case of a breeze. Can you list other examples of motion, besides those given here? A. Sheetal first went to her friend Sangita's house on her way to school, see figure 1.1b. B. Prashant went straight from home to school. Both are walking with the same speed. Who will take less time to reach the school and why? In the above example, is there a difference between the actual distance and the distance traveled? What is it? Think about it. Think about it. Displacement and distance. Let's try this one. O motion, O distance and displacement, O acceleration, O Newton's laws of motion and related equations. 1. Laws of motion. Sheetal and Prashant's house. Sangita's house. School 1300 m 500 m 1200 m 1.1 Location of the school and houses. A, B, 1. Measure the distance between points A and B in different ways as shown in figure 1.1, A, 2. Now measure the distance along the dotted line. Which distance is correct according to you and why? 1. The flight of a bird. 2. A stationary train. 3. Leaves flying through air. 4. A stone lying on a hill. Path A, path B. Can you tell? 2. Use your brain power. 1. Every morning, Swirly walks round the edge of a circular field having a radius of 100 m. As shown in figure 1.2, A, if she starts from the point A and takes one round, how much distance has she walked and what is her displacement? 2. If a car, starting from point P, goes to point Q, see figure 1.2b, and then returns to point P, how much distance has it traveled and what is its displacement? AQP registered 360 meters. Total distance traveled. Time required. Speed equals even if the displacement of an object is 0, the actual distance traversed by it may not be 0. Displacement time velocity equals 1. The units of speed and velocity are the same. In the SI system, the unit is m/s while in the CGS system, it is cm/s2. Speed is related to distance while velocity is related to the displacement. 3. If the motion is along a straight line, the values of speed and velocity are the same, otherwise they can be different. Velocity is the displacement that occurs in unit time. The distance traveled in a particular direction by an object in unit time is called its velocity. Here, unit time can be 1 second, 1 minute, 1 hour, etc. If large units are used, 1 year can also be used as a unit of time. The displacement that occurs in unit time is called velocity. 1.2 Distance and displacement. Can you recall? Always remember, A, B, distance is the length of the actual path traveled by an object in motion while going from one point to another, whereas displacement is the minimum distance between the starting and finishing points. 1. What are vectors and scalars? 2. Which of the quantities distance, speed, velocity, time, and displacement are scalars and which are vectors? Speed and velocity. Sachin is traveling on a motorbike. Explain what will happen in the following events during Sachin's ride, see figure 1.3. 1. What will be the effect on the velocity of the motorcycle if its speed increases or decreases, but its direction remains unchanged? 2. In case of a turning on the road, will the velocity and speed be same? If Sachin changes the direction of the motorcycle, keeping its speed constant, what will be the effect on the velocity? 3. If, on a turning, Sachin changes the direction as well as the speed of the motorcycle, what will be the effect on its velocity? It is clear from the above that velocity depends on speed as well as direction and that velocity changes by 1. Changing the speed while keeping the direction same too. Changing the direction while keeping the speed same 3. Changing the speed as well as the direction. Effect of speed and direction on velocity distance time Sheetal's speed along path A equals 500 m 5 minute equals 100 m/minute distance time Sheetal's speed along path B equals 1200 m 24 minute equals 50 m/minute total distance total time Sheetal's average speed equals 1700 m 29 minute equals 58.6 m/minute Sheetal's velocity equals 44.83 m/minute displacement time Sheetal's velocity equals 1300 m 29 minute equals 1.3 Effect on velocity in the first example, on page 1, the straight line distance between the houses of Sheetal and Sangeeta is 500 m and that between Sangeeta's house and school is 1200 m. Also, the straight line distance between Sheetal's house and school is 1300 m. Suppose Sheetal takes 5 minutes to reach Sangeeta's house and then 24 minutes to reach school from there, then, the first scientist to measure speed as the distance/time was Galileo. The speed of sound in dry air is 343.2 m/s while the speed of light is about 3 times 108 m/s. The speed of revolution of the Earth around the Sun is about 29,770 m/s. Always remember. Uniform and non-uniform linear motion Amar, Akbar, and Anthony are traveling in different cars with different velocities. The distances covered by them during different time intervals are given in the following table. Time in the clock distance covered by Amar in km distance covered by Akbar in km distance covered by Anthony in km 5.00005.30 2018 14 6.00 40 36 28 6.30 64 42 7.00 87 56 7.30 195 78.00 120 120 84 Let's try this. 1. What is the time interval between the notings of distances made by Amar, Akbar, and Anthony? 2. Who has covered equal distances in equal time intervals? 3. Are all the distances covered by Akbar in the fixed time intervals the same? 4. Considering the distances covered by Amar, Akbar, and Anthony in fixed time intervals, what can you say about their speeds? If an object covers equal distances in equal time intervals, it is said to be moving with uniform speed. Acceleration 1. Take a 1 m long plastic tube and cut it lengthwise into 2 halves. 2. Take one of the channel-shaped pieces. Place one of its ends on the ground and hold the other at some height from the ground as shown in figure 1.4. 3. Take a small ball and release it from the upper end of the channel. 4. Observe the velocity of the ball as it rolls down along the channel. 5. Is its velocity the same at all points? 6. Observe how the velocity changes as it moves from the top, through the middle and to the bottom. 1.4 Change in velocity. Use your brain power. Ball channel. If an object covers unequal distances in equal time intervals, it is said to be moving with non-uniform speed. For example, the motion of a vehicle being driven through heavy traffic. You must have all played on a slide in a park. You know that while sliding down, the velocity is less at the top, it increases in the middle and becomes 0 towards the end. The rate of change of velocity is called acceleration. Acceleration equals if the initial velocity is u and in time t it changes to the final velocity v. If the velocity of an object changes during a certain time period, then it is said to have accelerated motion. An object in motion can have 2 types of acceleration. 1. If the velocity changes by equal amounts in equal time intervals, the object is said to be in uniform acceleration. 2. If the velocity changes by unequal amounts in equal time intervals, the object is said to be non-uniform acceleration. Change in velocity time. Final velocity, initial velocity time, VU, t acceleration equals a equals backslash a equals positive, negative, and zero acceleration. An object can have positive or negative acceleration. When the velocity of an object increases, the acceleration is positive. In this case, the acceleration is in the direction of velocity. When the velocity of an object decreases with time, it has negative acceleration. Negative acceleration is also called deceleration. Its direction is opposite to the direction of velocity. If the velocity of the object does not change with time, it has zero acceleration. Distance time graph for uniform motion. The following table shows the distances covered by a car in fixed time intervals. Draw a graph of distance against time, taking time along the x-axis and distance along the y-axis in figure 1.5. Time, seconds, distance, meters. 7105 distance, meters, 1.5 distance, time graph scale, x-axis 1 cm 100 and y time. 1. When an object is at rest in the beginning of its motion, what is its initial velocity? 2. When an object comes to rest at the end of its motion, what is its final velocity? Use your brain power. An object in uniform motion covers equal distances in equal time intervals. Thus, the graph between distance and time is a straight line. In the distance-time graph above, what does the slope of the straight line indicate? Distance-time graph for non-uniform motion. Use your brain power. Here, the distance changes non-uniformly with time. Thus, the bus is having non-uniform motion. Time, second, distance, meter, 0, 0, 5, 7, 10, 12, 15, 20, 20, 30, 25, 41, 30, 50, 35, 50. The following table shows the distances covered by a bus in equal time intervals. Draw a graph of distance against time, taking the time along the x-axis and distance along the y-axis in figure 1.6. Does the graph show a direct proportionality between distance and time? What difference do you see in the distance-time graphs for uniform and non-uniform motion? Velocity time graph for uniform velocity. A train is moving with a uniform velocity of 60 km/h for 5 hours. The velocity time graph for this uniform motion is shown in figure 1.7. 1. With the help of the graph, how will you determine the distance covered by the train between 2 and 4 hours? 2. Is there a relation between the distance covered by the train between 2 and 4 hours and the area of a particular quadrangle in the graph? What is the acceleration of the train? 1.6 Distance, time graph. 1.7 Velocity, time graph. Velocity, km/hr, 0, 1, 2, 3, 4, 5, 50, 40, 30, 20, 10. CDT 1T, y-axis. Table. Time, seconds, velocity, m/s, 0, 0, 5, 8, 10, 16, 15, 24, 20, 32, 25, 40, 30, 48, 35, 56. The velocity time graph in figure 1.8 shows that, 1. The velocity changes by equal amounts in equal time intervals. Thus, this is uniformly accelerated motion. How much does the velocity change every 5 minutes? 2. For all uniformly accelerated motions, the velocity time graph is a straight line. 3. For non-uniformly accelerated motions, the velocity time graph may have any shape depending on how the acceleration changes with time. From the graph in figure 1.8, we can determine the distance covered by the car between the 10th and the 20th seconds, as we did in the case of the train in the previous example. The difference is that the velocity of the car is not constant, unlike that of the train, but is continuously changing because of uniform acceleration. In such a case, we have to use the average velocity of the car in the given time interval to determine the distance covered in that interval. Equations of motion using graphical method. Newton studied motion of an object and gave a set of 3 equations of motion. These relate the displacement, velocity, acceleration, and time of an object moving along a straight line. Multiplying this by the time interval, i.e. 10 seconds, gives us the distance covered by the car. Distance covered equals 24 m/s 10 s equals 240 m. Check that, similar to the example of the train, the distance covered is given by the area of quadrangle ABCD. 32 plus 16 2 equals 24 m/s ABCD. Equation describing the relation between velocity and time. Figure 1.9 shows the change in velocity with time of a uniformly accelerated object. The object starts from the point D in the graph with velocity u. Its velocity keeps increasing, and after time t, it reaches the point B on the graph. V equals u plus at. This is the relation between velocity and time. S equals ut plus at 2. This is the relation between displacement and time. V2 equals u2 plus 2, as this is the relation between displacement and velocity. Let us try to obtain these equations by the graphical method. Suppose an object is in motion along a straight line with initial velocity u. It attains a final velocity v in time t due to acceleration. Its displacement is s. The three equations of motion can be written as 1, 2. The initial velocity of the object equals u equals od. The final velocity of the object equals v equals oc. Time equals t equals oe. Change in velocity time acceleration, a, equals, final velocity, initial velocity, time equals \cd equals at, I, OC, OD equals CD, from the graph. B equals AB plus AE \V equals CD plus OD, AB equals CD and AE equals OD, \V equals at plus U, from I, \V equals U plus at. This is the first equation of motion. OC, OD, T equals velocity VBU 1.9 velocity, time graph time CDATEOB. Draw a line parallel to y-axis passing through B. This will cross the x-axis in E. Draw a line parallel to x-axis passing through D. This will cross the line B at A. VU, ta equals, VU, at equals 1, 2. Equation describing the relation between displacement and velocity. The velocity of an accelerated object changes with time. Change in the velocity can be due to a change in direction or magnitude of the velocity, or both. Always remember 1, 2, 1, 2 s equals ut plus at 2 \Newton's second equation of motion is \s equals u times t plus times at times t. We have seen that from the graph in figure 1.9 we can determine the distance covered by the object in time t from the area of the quadrangle DOEB. DOEB is a trapezium, so we can use the formula for its area. \s equals area of trapezium DOEB \s equals times sum of lengths of parallel sides times distance between the parallel sides. \s equals times OD plus B times OE, but OD equals U, B equals V and OE equals T. \s equals times U plus V, times T, 2, but, \-3, 1, 2, 1, 2 \s equals times, U plus V, times \2 as equals V plus U, VU, equals V2 U2 1 2, VU, A, V plus U, VU, 2as equals \V2 equals U2 plus 2, as this is Newton's third. Equation of motion. Let's try this uniform circular motion. The speed of the tip is constant, but the direction of its displacement and therefore, its velocity is constantly changing. As the tip is moving along a circular path, its motion is called uniform circular motion. Can you give more examples of such motion? Observe the tip of the second hand of a clock. What can you say about its velocity and speed? But, AE equals U, OE equals T and, OE equals D equals T, UB equals at dash dash, UB equals CD, dash from, I. Determining the direction of velocity in uniform circular motion. Let's try this. Find out more examples of circular motion in day-to-day life. 1. Determining the direction of velocity in uniform circular motion. Let's try this. Find out more examples of circular motion in day-to-day life. 1. Draw a rectangular path as shown figure 1.102. Place the tip of your pencil on the middle of any side of the square path and trace the path. 3. Note how many times you have to change the direction while tracing the complete path. 4. Now repeat this action for a pentagonal, hexagonal, octagonal path and note the number of times you have to change direction. 5. If you increase the number of sides of the polygon and make it infinite, how many times will you have to change the direction? What will be the shape of the path? This shows that as we increase the number of sides, we have to keep changing direction more and more times. And when we increase the number of sides to infinity, the polygon becomes a circle. 1.10 Changes in direction. 1.11 The coin and the disk circumference times speed equals 2 PRTV equals if an object, moving along a circular path of radius r, takes time t to come back to its starting position, its speed can be determined using the formula given below. R equals radius of the circle. When an object is moving with a constant speed along a circular path, the change in velocity is only due to the change in direction. Hence, it is accelerated motion. When an object moves with constant speed along a circular path, the motion is called uniform circular motion, e.g. the motion of a stone in a sling or that of any point on a bicycle wheel when they are in uniform motion. Try out and think about it. Take a circular disc and put a 5 rupee coin at a point along its edge. Disc coin research make it move around its axis by putting a pin through it. When the disc is moved at higher speed, the coin will be thrown off as shown in figure 1.11. Note the direction in which it is thrown off. Repeat the action placing the coin at different points along the edge of the circle and observe the direction in which the coin is thrown off. Example 1. An athlete is running on a circular track. He runs a distance of 400 m in 25 s before returning to his original position. What is his average speed and velocity? Given, total distance traveled equals 400 m, total displacement equals 0, as he returns to his original position. Total time equals 25 seconds. Average speed equals, average velocity equals. Solved examples. Total distance covered, total time taken, average speed equals Given, A equals 3.2 meters per square second. Example 1, an athlete is running on a circular track. He runs a distance of 400 m in 25 s before returning to his original position. What is his average speed and velocity? Given, total distance traveled equals 400 m, total displacement equals 0, as he returns to his original position. Total time equals 25 seconds. Average speed equals, average velocity equals. Solved examples: total distance covered, total time taken, average speed equals 425 equals 16 m/s, total displacement, total time taken, average velocity equals 0.25 equals 0 m/s. The coin will be thrown off. Example 1, an athlete is running on a circular. Example 2, an aeroplane taxis on the runway for 30 seconds with an acceleration of 3.2 meters per square second before taking off. How much distance would it have covered on the runway? Given, A equals 3.2 meters per square second, T equals 30 s, U equals O, S equals ut plus at 2 equals 0 times 30 plus times 3.2 times 302 equals 1440 m1212. Example 3, a kangaroo can jump 2.5 m vertically. What must be the initial velocity of the kangaroo? Given, A equals 9